Hello again, OChem students. Today we're going to talk about resonance structures, what they are and how to draw them. Suppose you have a formula and you're asked to draw the Lewis structure. You start to draw the Lewis structure of, for example, C3H5 plus charge, so it's a cation. And you find that you must connect together the three carbon atoms. You're going to have a pi bond between two of the carbon atoms and with the plus charge on one of the carbons. And this is one of the two valid ways to draw this structure. In this particular structure, you're implying that carbon 1 has the cation on it, and the bond between carbons 1 and 2 is a single bond. You could also write an alternative representation in which you show a double bond between carbons 1 and 2 and a single bond between carbons 2 and 3 and the plus charge on the 3. Which of these is the correct structure? Well, it turns out both of them are, or neither one of them are. If you can imagine that the real structure is somewhere between these two, it's a mixture of the two. To give you an idea what that might look like, here is a picture of the molecular orbital that represents the pi system for the cation. This area up here is a pi bond spread over 1, 2, 3 atoms. Those are the hydrogens sticking out underneath it. And that's the bottom half of the pi molecular orbital. In other words, neither structure 1 nor structure 2 is correct, but a mixture or hybrid of. In the next part of this video, we will talk about how to generate or draw resonance structures and how to recognize when a resonance structure, one or more resonance structures, is possible. Here I have three examples for which to draw resonance structures. The first is an allocation. You started off with your formula C3H5 and came up with the structure on the top. We know it's not the only structure that can represent the allocation, but how do you figure that out without just trial and error? Well, one way to think of it is to think of electrons, negative charge, want to move towards a positive charge. If you look at this compound, carbon 1, carbon 2 are pi bound. Carbon 3 is deficient in electrons. It has a positive charge and only 3 bonds around it. So you can imagine that this pair of electrons wants to move over to kind of even out the valence on the other side. That structure can be represented by the second resonance form. And to draw an accurate resonance structure, you need to have exactly the same sigma structure as the original. So it's 3 carbons bound together in a row. Each carbon has 2 additional bonds on it. Here I haven't specified the hydrogens from the allocation. They can be bonds to anything. And this is exactly the same blue sigma structure as we had on the left. However, the pi bond, the extra 2 electrons that are in the pi system are going to now appear between carbons 2 and 3. And that leaves carbon 1 deficient of a charge with only 3 bonds and no lone pairs. And there is your second resonance structure. This is the first of 3 kinds of resonance in which it's called pi bond empty orbital resonance. You have a system where you have 1, 2, 3 carbons in a row. 2 of them are bound by a pi bond, and the third has a positive charge, or at least an empty orbital on it, like this carbocation. The second major type of resonance is when you have a lone pair of electrons on one atom next to a pi bond on 2 additional atoms. So they're all again in a line. In this case, your negative charge, your excess electrons, is going to move away from that carbon because carbon doesn't want to have that extra pair of electrons. So you can imagine that pair of electrons going to make a new bond between the 2 carbon atoms. At the same time, the carbon atom bound to the oxygen can only have a total of 4 bonds. So the bond between oxygen and carbon has to move out of the way, away from the carbon atom that has the new pi bond. Once again, when you go to write a second resonance structure, it must have an identical sigma structure to the original. That is, all the blue bonds must remain. It goes without saying that when you're drawing resonance contributors to the actual structure, resonance forms, you have to follow all the rules of Lewis. You can't have more than an octet on a given atom. You need to put in pi bonds and lone pairs to maximize the octets, and you need to put in the correct formal charges. Okay, so according to these arrows, the pair of electrons that was residing on the carbon atom will now form a pi bond between the two carbon atoms, and the pair of electrons that was residing on the oxygen atom will now reside as an unpaired pair of electrons on the oxygen. Of course, oxygen already had two pairs of electrons to start with before we started moving things around. So let's go ahead and put those in. And so overall at the end, oxygen has 3 lone pairs, 1 bond, net formal charge of -1. And this illustrates something else as well as this does on the top about resonance forms. If one of the resonance forms has a charge, say -1, the other resonance form has to have a charge. That charge can be on a different atom, different formal charge, but the overall charge of the species needs to be the same. -1 for the second one, and +1 for the first. Now the structure on the bottom represents a third kind of resonance, and that's called pi bond resonance. It happens when you have a pi bond followed by no pi bond, followed by pi bond, followed by no pi bond. Or you can have, in this case, it's a whole ring full of alternating single and double bonds. This particular structure is called benzene, and benzene has 2 equally good resonance forms. Both of them have 1 carbon atom at each apex, 1 hydrogen atom at each position off the carbon, 1 additional bond. But the difference between the 2 representations is that the double bonds do not reside between carbons 1 and 2 in the second representation, but rather 2 and 3. They don't reside between carbons 2 and 3 in the second representation. They reside between 3 and 4. In other words, the alternate double bonds are shown in every position that only single bonds are shown in the left. These are the 2 resonance forms for benzene, and it is well known experimentally that benzene doesn't have double, single, double bonds. Its bond lengths correspond to exactly the same bond length on all of them, and neither of these Lewis structures adequately represents benzene. Or you could say both of them do if you combine them. Overall, benzene has a 0 formal charge